IASC. Today's talk is by Yunus Inan, and he will be speaking on age-distortion trade-offs. Yunus Inan received the BS degree in Electrical and Electronics Engineering from Bilken University, Ankara in 2018. He is currently pursuing the PhD degree in the Computer and Communication Sciences under the supervision of Professor Emre Talatar in the Information Theory Lab at EPFL, Switzerland. His research interests are in communication and information theories. Before we move on to the talk, we would like to request the online audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Before we move on, please keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, you may unmute yourself and ask Mr. Inan directly or type them in the chat box. We'll relay your question. Over to you, Mr. Inan.
Okay. Can everyone hear me?
Yeah.
Okay, perfect. So, hello everyone. I'm Yunus. Welcome to this talk on age-distortion trade-offs. And it's a pleasure for me to give this talk in the context of network seminars. So I'm Yunus. I'm a PhD student at EPFL, affiliated with Information Processing Group. And this talk will be based on a joint work with my colleague Reka and with Professor Talatar, who is our advisor. So let us start the talk. Sorry. Okay. First of all, it's important to touch upon the rate distortion theory, the classical rate distortion theory in the information theory literature. So as you may know, the rate distortion theory was first proposed by Shannon in his work titled Coding Theorems for Discrete Source with a Fidelity Criterion in 1959. So to briefly describe the rate distortion setting, we have an IID source, x1 up to xt, and we want to represent this source with at most RT bits. So if we check the scheme here, we have the source, which has maybe some data generated until time t, then the encoder takes in the source, spits out and message, which takes values from 1 till 2 to the RT, which can be represented by R bits, and then the decoder receives the message and consequently obtains the reconstruction, denoted by X hats. So in classical information theory, the lossless coding, we know that if the rate is smaller than the entropy of the source, it's impossible to obtain a perfect reconstruction of the source. So Shannon tried to study a trade-off between low rates and a possible fidelity criterion, which aims to represent the source as good as possible. So what is this fidelity criterion? Shannon tried to capture this fidelity by the following additive distortion metric in the simplest setting. So we denote this by D. If you look at it, it's basically a time average of the individual discrepancies between the symbols. And of course, since this is a stochastic entity, in the end, we take the expectation. So to interpret this formulation, we can think of some symbols having some importance, and misrepresentation of these symbols result in some penalty. And Shannon tried to capture this fidelity criterion by incorporating the penalty of misrepresentation into this distortion metric. So again, recall that if the rate is smaller than entropy, it's impossible to reconstruct the source exactly. Hence, Shannon asked the question of what is the best distortion and rate trade-off we can achieve when rate is smaller than entropy. The answer is given by the rate distortion curve. What do we mean? The answer is something like this. For any encoder-decoder pairs, the possible distortion rate pairs, they lie in the feasible region shaded with red, as seen as here. So this scheme actually corresponds to the problem where we have IID Bernoulli bits and the distortion is basically Hamming distortion. Consequently, we obtain a trade-off between the rate and distortion as seen in the figure. So this means that the area under the rate distortion curve is not at all achievable. It's impossible for any type of scheme, as we described in the previous slide. But the good thing is the boundary of this optimal curve, the boundary of the rate distortion curve, R of t, can be approached at very large t. And this is shown with very simple random coding techniques. But this means that the decoder obtains the reconstruction very late, right? Because if t is very large, then the encoder waits for a long time to encode the source, and then the decoder will consequently obtain the reconstruction at a very late time. So this may create a problem for stringent time requirements, right? If our replication must be low latency, then this may create a problem. So according to this observation, we can ask the question, is there an implicit trade-off lying between the rate, distortion, and timeliness? Such as in this plot. By the way, this is a hypothetical plot just to illustrate a possible trade-off. So for instance, if the time conditions are relaxed, so if we allow the encoder to wait more, then the rate distortion curve approaches the origin. And when we have more stringent time conditions, that means that the encoder mustn't wait too long, then we may have a curve, rate distortion curve, which is much further than the origin. But still, how to measure or assess the timeliness of such compression schemes, we don't know exactly. But there is a popular metric now in the information literature, which is called the age of information. So this age of information is a metric to assess timeliness, and moreover, it's a receiver-centric metric. This age of information was first proposed by Cole and al. In 2012. So to describe this, what age of information is, consider the following sender-receiver pair. Suppose that at time t, the sender possesses the data in his memory, denoted by mt of s, these data. Okay, so basically this means that in sender's memory, we have these packets, x1 up to xn, and these packets have been generated at times t1 up to tn, if we sort by increasing order. Similarly, the receiver has in its memory some data, which we denote by x1 up to xm, and again, generated at times r1 till rm. And we use the superscript r to denote that this data is processed by the receiver. Another thing is, since we know that the data, of course, flows from sender to receiver, we always have the condition that the memory of the sender includes the memory of the receiver, right? In other words, it will be a superset of the content that the receiver possesses. So now we can define the instantaneous age, instantaneous A of I, according to the setting. It is basically defined as this quantity, delta of t, is equal to t minus tm of r. What is that? So this is basically the current time, because recall that we are now at time t, the current time minus the generation time of the receiver's most recent data or packet. So recall that the packets in the receiver's buffer are ordered by their timestamps, their generation time. So this XM of R must be the freshest data. So that's why the age is defined as this quantity. So let us move on with a very canonical example in age of information literature. In this simple example, we assume that the packets arrive to the sender as a point process. For instance, assume Poisson process with its parameter lambda, with a rate of lambda. And then these packets are forwarded through a queue, single server queue. And you can assume an exponential service time, for instance. And in this very simple setting, we don't have any smart strategy at the sender side. So what does the sender do? When it receives a packet, it just forwards it into the queue. And here is a schematic of the system. So based on this, let us study the evolution of age of information, instantaneous age in this case. So as you may see, here is the definition of instantaneous age, and we assume that at time 0, the instantaneous age is 0. But in the end, if you want to study the long-term behavior or long-term average of the age, the initial conditions do not matter too much. But still, for simplicity, let us assume that at time t, the age is 0. And in light of this formula, the age grows linearly, and then after some point, it drops to this value. When it drops, when does it drop? It drops when the receiver receives its first packet. And to what value it drops? It drops to this value, which is the current time minus the generation time of the packet 1, right? According to the definition of instantaneous age. And then again, it increases linearly until the next reception happens. And again, when the next reception happens, when the receiver receives the packet number 2, the instantaneous age drops to this value, which is the difference between the reception time and the generation time of packet 2. And the evolution of the age continues on and on in a similar fashion. After we describe this the setting, we can slowly move towards the problem definition. So, in contrast to the previous case, we now consider a different scheme, which is in a discrete time setting. So, in this setting, we assume that the packet flows are controlled by an external scheduler. We'll describe this more. And now suppose that the sender receives or observes packet at each time instant, 1, 2, 3, 4, 5, 6. And what does the scheduler do? The scheduler polls the sender at some time instances, which we denote as speaking times. And at this speaking time, the sender is commanded to send something from its memory, some packet from its memory. So here's a representation of the scheme. Suppose now we're at time t, small t, and the scheduler commands the sender to send something. This means that t is a speaking time. At this time, suppose that the sender's memory contains these packets, these data, and the sender wants to choose among these x of I, which is shown by red. Consequently, the sender chooses and sends the x of I, and the receiver receives the data and puts the data in the corresponding place, as this. So you may ask, what are these question marks? These question marks basically represent the unseen data by the receiver. The data that have not been seen by the receiver, and these may not be seen forever. So these may remain as question marks forever. Now we can ask the following question. If the packets are of similar importance, the strategy that minimizes the age is obviously to send the freshest packet. But what if some packets have more importance compared to the others, right? Then instead of sending the freshest data, one may want to know about a past important event instead of a trivial most recent event.
Yunus, I have a question.
Yes.
Can you please go back to the previous slide?
Okay.
How
This
does
one.
the sender choose the packet? Like the XI, is it like randomly it selects anyone, or how does it send? Choose?
It can choose anything at the moment. Basically, this you will see that these will constitute the sender strategy. So right now we can just assume that it sends something from its memory. Is it clear?
Yes. And
Okay.
can you just elaborate a little on speaking times? What exactly is speaking time?
Okay, a speaking time is we have said that the scheduler imposes a rate control, right? Rate control procedure. So that's why at some certain times it tells the sender to send something. So the sender cannot be is not able to send every observation it has because of this rate control. And this rate control is governed by the speaking times assigned by the scheduler. So for instance, suppose we start the scheme like time 1, 2, 3, 4, and at time 5, the scheduler commands the sender to speak, and we say that this time 5 is a speaking time, and then sender follows a certain strategy. Is it clear?
Yes, thank you.
I have
Okay,
two
perfect.
questions.
Sure.
Yeah, so I guess so. Two things. First of all, are you assuming that each message is sent in the fixed rate R code word?
Sorry, can you repeat again?
Each XI, are you sending in a fixed R rate code word, or you have different size code word for each message?
Okay. So now our rate R is governed by the packet rate. So the number of packets, I mean, like, for instance, the average number of packets sent in a time period. So this will be our rate in this problem. And we assume that these XIs are formed into a packet. So we can consider these XIs as one unit. Is it clear? So the rate for our problem.
So maybe there are many questions here. Then I guess so. XI is not a real number.
No, XI is not a real. Yeah, XIs are packets.
XI as a packet means like XI as a bit. You're thinking, or?
Sorry, can you repeat? Yeah, XIs are big. Yeah, XIs are big. Yeah.
No, XI is a bit or XI is a packet. I'm not completely sure. XI is a bit, like 0, 1, or?
No. It's a packet. It's a data. So it can basically, if you think of these as symbols, it can take a huge amount of.
It's a large alphabet.
Exactly. Yeah, exactly.
But you're not doing quantization. You're sending as it is, whatever. Like it takes from alphabet, say script X, then you're gonna send XI as is.
Exactly. Yes, and the values X can take might be very big.
No, yeah, it doesn't matter. But you're sending it as is, and you're assuming there's no error in the channel.
Right? Yes, exactly. There is no error.
Only thing you do is that if you decide not to send, you don't get it. But if you send, you receive it perfectly.
Exactly.
Right?
Exactly.
And another thing which you said is that you have a rate control, as that means that the total amount of this, the symbols you can send is sort of limited, right? That you cannot send more than this in fixed number of time. That's what your rate constraint is, right?
It's actually the rate constraint is given in terms of the packet, the number of packets you can send.
I mean, packets, I'm thinking of as a symbol, each XI. So basically, the number of symbols you can send in a fixed time T, that is limited by, like average over time, and taking T10 is less than equal to some number, right? That's your constraint, I'm guessing.
Yes. But this rate constraint is imposed by the external scheduler. So by assigning the speaking times. So for instance, if the scheduler assigns speaking time.
So for example, I mean, this speaking time could also be a choice, design choice. Right now, you're saying that somebody tells you when to speak, but this could also be a choice, right? You can decide when to speak, when not to speak, right?
Exactly.
But that you're not solving that question.
No, at this moment, this control of speaking times are not given to us.
Okay, thank you.
Okay. So any other questions? Okay. Now we can move forward, I think. So we have some motivation on the problem. For instance, some packets assume that the sender contains measurements from a temperature sensor, and some packets may contain abnormal measurements or spikes in the temperature. So instead of sending the most recent measurement, the sender may opt to send a measurement from past, and which is important, which may correspond to abnormal measurement. The second example could be a fraudulent activity monitor, and instead of sending the freshest, most recent transaction between accounts, it may choose to send more suspicious transactions from past. And the last example could be a news feed where the sender might want to choose and send a breaking news, not the most recent one. So in such cases, the freshness, the age can be sacrificed for the sake of mitigating risks or acquiring important information. So now we can move on to the problem definition. And again, we go over to the same setting. Now, in addition to the previous setting, we assume that the scheduler polls the sender at speaking times, which we denote by T1, T2, etc. And the interspeaking times are IID. The interspeaking times are basically the difference between the speaking times. And we assume that the interspeaking times are square integrable, which is given by this condition. And at each speaking time, as you mentioned, the sender chooses a packet with timestamp S of I, SI, for instance, this one, and we further impose that the packets should be chosen in order. What does this mean? This means that the selection process SI should be increasing. So to illustrate what this means is that suppose that at speaking time Ti, at ith speaking time, the sender wants to choose this packet, and then at a later time, these packets cannot be chosen, right? So eventually these will contribute to our distortion, as we will see. Here's an important remark here, which we'll touch upon later, is that the timestamps are included in the packet header, right? And that's why the receiver is able to put the received packet in its corresponding place. So we also assume that the packets, they contain large content. The payload is large compared to the timestamp. So that the representation of the timestamp is very small compared to the payload. Okay, continuing with the problem definition, we assume that each packet has a cost of not being sent, which we denote by VT. So this VT we can see as importance values of a packet. So if the packet contains an important information, then its cost of not being sent will be higher, right? And we can also relate this quantity with the distortion metric, erasure distortion metric, more specifically, and we assume that the importance levels are in a finite set. And we further assume that the importance of the packets are IID process, but this can be extended to Markov processes, and maybe there may be further generation as well. So now the total distortion at time t in our setting is consequently given by this quantity, det. And to summarize what this is basically the sum of the costs of packets of data that have not been yet observed by the receiver. And this indicator function indicates that. But here's an important remark. Actually, these question marks at a later time can change. So this quantity is not actually a stochastic process. That's an important observation. And the instantaneous age, delta t, is given by t minus si. So basically, the current time minus the timestamp of the freshest packet that receiver has. So to relate with the RD time trade-off, we have seen in the previous slides, the rate is controlled by the external scheduler. If you assume that the rate is the packet rate, right? And it's equal to the 1 over mean of z, because the sender is able to send at each speaking time, and this is governed by the reciprocal of the speaking time in the long-term average. In addition, we have the distortion metric d, which is the expectation of the long-term average of dt's. So it is the average cost of the packets that are not sent or not seen by the receiver. And the timeliness is assessed by the average age of information. Again, the expectation of the long-term average of instantaneous ages. So now we can ask the following question. We have seen that at each speaking time, the sender can choose anything from its past with the condition that the packets arrive in order. Among all possible such selection processes, what is the best achievable delta and d trade-off? We pose this question and we attempt to solve it. So we will see that this problem eventually can be formulated as a Markov decision problem, which we abbreviate as MDP. A first attempt can be to consider d plus eta delta lines, right? A weighted cost between age and distortion. And since we have these lines and sweeping over all eta, this will give a convex curve, and consequently that gives a lower bound to our achievable region, because the achievable region is not necessarily convex, but since we obtain a convex curve by sweeping over all etas, our achievable region will lie on the top of this convex curve. Furthermore, thanks to the problem structure, I would say it turns out that we can only focus on time ticks taken as speaking times. What does this mean? Instead of taking the actual time axis, like 1, 2, 3, 4, 5, we consider the time ticks are taken as speaking times. So our time axis becomes T1, T2, T3, etc., where TIs are speaking times. And we have one technical condition which tells that at each speaking time, our selection process must preserve the square integrability condition like this at all times. And if this technical condition is satisfied, we have the following theorem, which gives a lower bound to a certain d plus eta delta line given by this. So in this formulation, in this theorem, this quantity j of eta is a long-term average of ji's, and ji's are given as the total cost until ith speaking time. If you have ji, this ji denotes the total cost obtained until the ith speaking time. total expected cost. And then this is the long-term average. So theorem 1 gives a lower bound to our weighted average costs. And this theorem follows from a lemma called reverse Fatou's lemma that allows us to change the limits, lim sup and expectation, etc. So now we have this lower bound, further lower bound, which we call by J of eta. And minimizing J of eta over the square integrable selection processes, we can formulate this problem as a Markov decision problem. And I also want to remark that these MDPs and its variants are encountered in age of information literature a lot, frequently. So I want to also briefly mention what an MDP is. So MDP is actually an optimal control of a Markov chain. And we have the control of actions for each state. So we have a Markov chain consisting of some states, and for each state, we have possible actions, and these possible actions incur a cost to the next step, plus a new transition map for the next state. And suppose the Markov chain is finite, finite states are finite, actions are finite, then in fact, one can find with brute force the best strategy, right? Because we have a finite space optimization problem. But it turns out that for our problem, the state space is infinite, but we will overcome that later. So coming back to our problem consists of states, which are the sender's memory at ith speaking time, which we denote as this quantity. As you remember, at ith speaking time, which we denote by Ti, the sender has observed these packets, right? The packet generated at time Si minus 1 plus 1 till the packet generated at the speaking time. We don't have to consider the past because according to the packet in order packet strategies, we cannot send anything from further past of this packet. So we eliminate those part. And since our distortion metric consists of the cost of not being sent, our state can be represented as the costs of packets contained in the buffer. And the actions correspond to which packet to choose at each speaking time. In other words, at ith speaking time, we want to choose an Si, and Si must take values in the set. And the one-step cost, the final ingredient for MDP, is the cost of skip packets in the buffer, because we cannot send them forever, right? If we choose a packet generated at Si, we cannot send these packets. So these contribute to our total distortion cost plus eta, the weight, times the cost of age, which is the current time, the ith speaking time minus the ith selection time. So going deeper, we now encounter an average cost, countable state space, Markov decision problem. And we have a possibly infinite state space because of possibly unbounded buffers, right? We didn't truncate, we didn't use any truncation on the buffer. It can grow unboundedly. And in general, this class of problems are difficult to solve. But luckily for our problem, we could show that the optimal strategies can be attained within a bounded buffer. So what does this mean? Actually, we will see in this theorem 2 better. So for a given eta, a given weight, a buffer of size k of eta is necessary and sufficient to attain the optimal strategies. The important thing in the definition of k of eta is that it's reciprocal with eta, right? So this means that when eta is small, which means that we give less weight to the age and we allow higher ages in our strategy. So this will result in higher buffer sizes, which will create problems in numerical results. Furthermore, since we have shown that we can attain the optimal strategies in a finite buffer. These finite buffer strategies constitute renewal processes. And renewal processes have nice ergodic properties. Ergodic are the properties that imply that the time average converges to something. And this actually implies that the inequality in theorem 1 becomes inequality. As you remember, the inequality in theorem 1 was exactly the same, where we had inequality instead of equality, but for the finite buffer strategies, this becomes inequality because we can also have the same lower bound in the right-hand side as an upper bound to d plus delta line. So this d plus delta, these d plus eta delta lines are squeezed in between j opt. So this will be an inequality in the end, equality in the end. And since, again, we have finite strategies, finite buffer strategies, we can characterize these with numerical methods such as policy iteration methods or value iteration methods. And consequently, we can find the optimal trade-off. However, we have a problem here, right? As I mentioned in the previous slide, since the necessary buffer size grows with 1 over eta, or low eta or high age regime, it's nearly impossible to calculate the optimal trade-off curve with numerical simulations. There is no computational power for that. At least we didn't have. So for this example, for instance, we could only calculate the optimal curve until this point. So in this example, we have the following. The interspeaking times are geometric random variables with success probability 0.2. And we have two types of packets: the unimportant ones and important ones. So the unimportant ones have a cost of not being sent equal to 1, and the important ones have a cost of 20. So the unimportant packets arrive with a rate 0.7, whereas the important packets arrive with a rate of 0.3. So according to the setting, if we calculate the optimal curve, it looks like something like this. And here, the blue solid lines are actually the eta delta lines, and then we sweep over eta until reaching some particular value of eta, because after that, the buffer size is too large. And in fact, we could only calculate this curve until a buffer size of 17, because the state space grows exponentially with the buffer size, and the algorithm becomes too complex. But still, since we know that any single tangent line gives a lower bound to our curve, extending this final line, we obtain a lower bound to our region. Furthermore, we compared with a very simple ad hoc strategy, which we call by S. So this S corresponds to the strategy: send the oldest important packet among the most recent K ones. Okay, so intuitively, when K increases, the sender is able to choose important data from further past, right? So the age grows. So the age delta is increasing with K, and when we vary K, we obtain this curve. But still, around this region, we don't know yet the exact behavior of the optimal curve. And also, I want to note that what this d-min is. This d-min is a basically universal lower bound for the distortion value. It's obtained very simply, but I won't go into details for that. So now, as we discussed, recall that the timestamps were contained in the packet headers, right? And the packet content is large such that the timestamp description or packet header is negligible compared to the packet payload in the previous setting. But what if the payloads become very small, right? For instance, 1 bit. And this actually corresponds to a bit stream arriving to the sender. Now we can in light of the question asked before, now we have 1 bit contained in the buffer. Okay. And so what would our naive strategy do? Our naive strategy would do the following: choose a bit from the memory, wrap it with the timestamp description, and then form a packet of length 1 plus the length of the timestamp, right? And since the timestamp is probably more difficult to describe than the single bit, the the packet header will be very large compared to the payload, which is 1 bit. So is it a reasonable strategy to do? Of course not. And now we can study this extreme problem where we have 1 bit, and we call this the bitstream problem. It's basically something like this. At each time instant, the sender receives a bit. And assume that the bits arrive as IID Bernoulli bits, where they have a cost of not being sent. So this can be also represented by an asymmetric distortion metric. So D of 0 question mark is the cost of a bit 0 not sent, and distortion 1 question mark is the cost of bit 1 not being sent. All right. And furthermore, now we allow the sender to speak n bits at speaking time, not just 1 bit. So a possible strategy could be to consider sending contiguous segments of n bits among the buffer. What does this mean? For instance, let's illustrate with an example. The sender's buffer can be something like this at I speaking time, and the sender wants to choose this segment in its buffer. And in this example, n is equal to 6 because the sender is able to send 6 bits. So again, at the same speaking time, the receiver's buffer is empty. It doesn't know anything. So just after the I speaking time, the sender updates its buffer accordingly, like this. Why? Because after sending this segment, since it cannot send anything from the past, because still we want the order preserving strategies, the sender updates its buffer and puts the tail here. And just after the I speaking time, the receiver's buffer will look like this. The receiver is able to put the corresponding segment, received segment, in its corresponding place. And these 4 elements are kept for the next speaking time. But here you may have noticed a problem, right? How does the receiver know where to place the segment? This implies that still the receiver somehow needs a timing information or timestamp in order to place the received bits to the correct place. So here we have an important observation. Since the receiver tracks the sender's strategies, it has to track the sender's buffer length at all times, right? So it knows the sender's buffer length at all times. And we aim to use this share information. So, for instance, if the buffer is chosen, if the tau, the timing information, is chosen with respect to only the buffer length L, then the receiver will readily know what tau of L is. And then, after the reception of the segment, it will be able to place the segment in its corresponding place. So you may have noticed that the title is buffer ignorance strategies for these type of strategies. Why? As you may have noticed, the sender doesn't look at the content of the buffer, right? It just adjusts a shift tau depending on its length, and then sends the remaining n bits. So that's why we coined the term buffer ignorant for such strategies. Okay, now we have described that what a buffer ignorance strategy is. It's basically finding the optimal function of tau, depending on the length of the buffer. And this problem can be solved with similar MDP formulations. One can also show that, again, we need finite lengths, as in the previous part, so we can resort to finite state methods, such as policy iteration, etc. And then we obtain curves for the optimal buffer ignorance strategies. So let us compare with the previous naive example. Again, this curve corresponds to the same example we have seen in the previous slides. We have the same setting. And recall that for the previous strategies, the naive strategies, we could only calculate within a buffer size of 17, right? So in terms of bits, this will correspond to 6-bit packets, which contain 5 bits of timestamp description, because log 17 is approximately 5, and plus 1 bit for the content. And this naive strategy, again, gives this curve, as we have seen, but comparing with the optimal buffer ignorance strategies, for instance, if we have a 6-bit buffer ignorance strategy, we have a curve like this, which significantly outperforms the naive strategies. Furthermore, even if we halve the number of bits, if we allow the sender to speak 3 bits at each speaking time, the curve becomes the dashed line, the dashed curve here, right? It's still dominates the naive strategies, even if we use the half number of bits. So now we give a method to improve the buffer ignorance strategies, again, in an ad hoc manner. So the simplest thing is, of course, partially revealing the buffer content, right? Because buffer ignorance, they don't care about the buffer content, so we sort of want to reveal the buffer content. Okay, how do we do that? We do as follows. At the sender side, again, we received tau of L bits in the end. Again, similarly to the previous buffer ignorance strategies. And then we reveal the remaining bits one by one. And we start from the most recent one. Like here, for instance, we reserve the last 4 bits and then we go 1, 1, 0, 0, 0, etc. Okay. And we stop at some point. How do we stop? We stop according to a variable to fixed length coding method. And for instance, we use Tunstall coding for this, for the improvement. Again, an example of a Tunstall codebook for 2 bits, and if the bits are if the bits are 1 with probability 0.7, and if the sender is able to speak 2 bits, then we should have 4 possibilities in our codebook, right? So the Tunstall codebook, according to these parameters, when generated, will look like something, will look like this. So this tells that whenever we encounter 111, 110, 10, or 0, we stop and encode the representation in a symbol, in a 2-bit symbol. Again, here, for instance, once we observe 1, 1, 0, according to Tunstall codebook for 2 bits, we encode this 1, 1, 0 and then forward it to the receiver. And as one may guess, there's an improvement with Tunstall coding. So these blue curves correspond to the Tunstall improved version of the buffer ignorance strategies. And it's not a surprise that they improve. Now we move towards the end of the talk. And here I want to summarize some points. So first of all, in short, we studied a discrete time system where the trade-off between distortion and age or timeliness exists, can be seen. And in the packet-based problem, the first version of the problem, we have found the optimal policies are attained with finite buffering. And consequently, we were able to find the optimal strategies with numerical methods until some buffer size, of course. After that, when the buffer size gets large, there's no computational power for that. So we still don't know how the curve exactly behaves asymptotically. And after this packet-based problem, we talked about the bitstream problem, where we discussed the buffer ignorance strategies, and we have shown that they can be improved with coding, for instance, tunnel coding. And again, the numerical simulations show that these type of improved strategies significantly improve the packet-based strategies, the naive strategies, when the packet payloads are small, and in particular, 1 bit. So as further directions, again, as addressed in some of the questions in the talk, the sender might be control the speaking times, might be able to control the speaking times as well, right? So for related frameworks, one can see the following works we have given as references. But still, for the bitstream problem, we think that, I think that actually we might be far off from the optimal trade-off curve. And one may study more sophisticated coding strategies, because what we have done was basically following an ad hoc approach, buffer ignorance strategies. We found the optimal buffer ignorance strategies, and we have shown that they can be improved with some coding. But still, it may be far off from the optimal. And thank you for listening and attending, everyone. And I hope you enjoyed the talk. If there are any further questions, I'm happy to answer. Any questions so far?
Thank you, Mr. Inan, for an informative talk. We can take 1-2 questions more and close. If there is any more questions, please do ask. The link to the slides will also be posted in the web page. Thank you and have a great evening.
Okay, perfect. Again, I want to thank you for giving me this opportunity to present our work, and it was a pleasure to give this talk.
Thank
so
you.
I believe we end this now.
Yeah.
Okay, perfect. So have a nice day and enjoy the rest of the day.
Thank you.